So what I want to talk about today, I want to get into inverse functions, what logarithms are, and then inverse trig functions. So I'm going to get into inverses first, and then what I'm going to try to get into 2.1 today also. So it's kind of a packed day. Now, if you want more details on logarithms, I can post a video on logarithms, and if that's going to help, it kind of goes into kind of the nitty-gritty of what they are and how to work with some more complicated problems. But first off, I want to talk about inverses. And so the idea of an inverse goes like this. So you have an input x. It goes into a function f. And then you get an output y. So the thing about an inverse is, what if we want to go the other direction? So what we'll do is we'll go to y, and then we're going to go back to x. And it's the inverse function that takes y back into x. So I'll just give you an example of how this works. Two functions that are inverses of each other. So we have f of x is x cubed, and then f of inverse, the inverse of x, the cubed, is x to the 1/3. So let's say we choose x equals 2. Well, then f of 2 gives us 8. So this is going to be our y. Now let's take this y value and put it into the inverse. So f inverse of 8 is the 8 to the 1/3, or the cube root of 8. And then we get back our 2, which was our x. So we took our y value, we put it into our inverse, and there we go. So that's the idea of an inverse. We start with an x value, apply f to it, we get a y value. Take that y value, apply the inverse, we get the original x value back. So inverse functions have some properties. The first one is composition. So if two functions are inverses of each other, if we compose them, means we place the inverse inside the original function, we just get x. And likewise, if we place the original function inside the inverse, we also get x. And both of these need to be true. If you have a function where only one of these works, then you actually don't have inverses, you have something else. But both of these need to work if the functions are in fact inverses of each other. So just to show, f of x is x cubed, f inverse is x to the 1/3. So if we do this, we're going to take x to the 1/3, and then we're going to cube it. And if you remember the property with exponents, we're going to multiply 3 1/3. That's just going to be 1. So x to the 1 is just x. Likewise, So we're going to take x cubed, which is our f of x. We'll take the cube root of it, or we'll multiply by the exponent 1/3, multiplying the exponents. Again, 1/3 of 3 is just 1, so x to the 1 is just x. So there we go. So x cubed, x to the 1/3, they're inverses of each other, and they have this property. So that's one property with inverses. The second property is that the domain and ranges switch. So if we have a point that's xy for f of x, for f inverse, we're going to get points y comma x. Now, when we graph an inverse function, we still graph it on the same Cartesian plane with a horizontal x-axis and a vertical y-axis. It's just the numbers here are going to switch. So just to show you what that looks like, so if we take f of x, actually let me do this, twos. So if we cube -2, we're going to get 8, -8. If we cube 0, we get 0. If we cube 2, we get +8. Now I'm going to talk about x and y for the inverse. So the way x and y switch here, these are the x and y values that came from f of x. Now f inverse has its own x and y values that still follow the same sort of format, where x is first and y is second. What we're going to see is that the numbers are going to switch. So if we take the cube root of -8, we get -2. Cube root of 0 is 0. Cube root of 8 is going to be 2. So we can see that say x is -2, y is -8. Now x is -8, y is -2. The numbers have switched is what's happened. So if we graph this, and if I'm going too fast, let me know. I can slow down. So let's see, we have -2, -8. Right here. 0 and 0. And then 2 and 8. Now, if I graph the inverse, this is f of x. Here's the inverse. Barring some artistic license, unfortunately. Fix this a little bit. So one of the properties we're going to have here, if we take a look at these two graphs, they're reflections of each other across the line x equals y equals x. Again, barring some artistic license here, they should be crossing at 1 and 1 here. I'll just make this note that geometrically it doesn't look like it. It's supposed to be 1 and 1. Same with this one, it should be crossing a little bit more here. So what this means, this is our third property. They're going to be reflections of each other across the line y equals x. Now there's one more property I want to mention with these, and it's called the horizontal line test. And this tells us if the function, the inverse, is going to actually be a function. F of x can be a function. We need to revisit what a function is. So a function is this. Oh, shoot, sorry, I'm the wrong definition. Let me go back. Just trying to remember which one it was. Okay. So I know how to state it. Oh, shoot. Sorry about that. I'm getting confused with the horizontal line test. I need to remember exactly what I want to say. Let me start that again. Having a little bit of a Monday today. What a function is that when you put x into f, you get one value out of it. You don't get, say, like 2, because you run into a situation called ambiguity. So if you put in x, say, which of the 2 or 3 or 4 values are you going to get? You don't know. So that's why we want to make sure we try to deal in functions. So we get an input, we put in an input, we get a particular output. Now, for the horizontal line test, we'll talk about that. This is our fourth property. So f inverse is a function if f passes this thing called the horizontal line test. So again, the idea of a function is you have an input, you should only get one output. Again, this comes from, say, like, it's an area of interest we get, say, from like mechanics. At a moment of time, you're only going to have one location for a particular object. It's not going to be in 2 places at the same time. So your input is time, your output is the object's location in space. So that's why we're interested in functions. So how does this horizontal line test work? Well, let's go back to x cubed. So if f of x equals x cubed. So the inverse function looks like this. So we have something like this. Now, the horizontal line test says if we take a horizontal line and we pass it through every point along the graph, every horizontal line only intersects f of x at one point. So this horizontal line, 1 point. Horizontal line, 1 point. 1 point, 1 point. So what that's going to mean is that the inverse is going to pass the vertical line test. The vertical line test is how we tell something is a function. And again, it's the idea that with one input, you only have one output. So with the vertical line test, every vertical line intersects our function only once. So this means the inverse of this is going to be a function. So that's the significance of the horizontal line test. And of course, since that's the case, then when we graph this inverse function, it better pass the vertical line test that tells us that it is in fact a function. So that's what's going on. We use the horizontal line test to see if this thing has an inverse that is in fact a function. And if it passes the horizontal line test, we're good to go. Just to kind of bring back though what the vertical line test was, it's a way of just verifying that it is in fact a function, but there's a little bit of extra. All right, any questions about that? Let me show you one where this doesn't work. So let's say we have this. So f of x equals x squared. Now in the text, they typically have some restriction on the domain. They'll say, for example, x is greater than or equal to 0. But in this case, we're going to go with everything. We're going to use all the x values. Now if we run the horizontal line test, all you need is one horizontal line to intersect this graph more than once. So here's a fail. This line creates a fail. It'll pass here at the vertex, but just because it passes once, that's not good enough. It has to be able to always pass. So what this says is the inverse So this says the inverse is not a function. Now the horizontal line test doesn't tell us anything about whether the function is a function. It just tells us the inverse isn't a function. This is in fact a function. If you gave it the vertical line test, every vertical line would intersect this graph at only one point. So it passes the vertical line test. It is a function. Its inverse isn't. So it's possible for functions to have inverses that are not functions. So what does the inverse look like? Unfortunately, the inverse is going to look like this. And if you give this the vertical line test, and the vertical line test tells us if something's a function or not, fails. And let me write this here. This is the inverse of y equals x squared. Now, what's going on here as far as inputs and outputs? Say, for example, you have this input. The x-axis tells us the inputs, so here's all the inputs. Y-axis gives us the outputs. So we have one input, but we have this output or this output. Well, which one? Are we here or are we here? So again, we're in two places at the same input or the same time, and that's not going to work. So this is not going to be a function. But we knew that already because the y equals x squared didn't pass the horizontal line test. This is just a little bit of extra credit, just going a little bit farther. Anyway, so those are four properties with inverses to keep in mind. All right, so finding inverses. And oftentimes we find inverses usually with lines. We do this with lines all the time. So let me pull an example from the homework. Let's see here. Well, they go a little bit farther, which is kind of cool. So let's say this. To find an inverse, there's several steps. For one, let's say we start out. We usually give an f of x. We change f of x to y. Then what we're going to do, we swap x and y. So instead of y equals something, we're going to get x equals something with a bunch of y's in it. Then we solve for y. So this is how we're going to find inverses. So let's say we have something like this. So first step, we rewrite f of x as y. Then we swap x and y. So we're just switching the labels. And now what we're going to do is we're going to solve for y. So again, x minus 1 is 2y. Divide both sides by 2. X minus 1 divided by 2 is equal to y. And so you could just call this your inverse. And then actually there's one last thing we do. You can say there's a fourth step. We relabel the y as f inverse. Questions about that? All right. So let's see, let's pick one here. So let's say we have this. And we're supposed to find the inverse. Again, we could relabel this as y. Switch out the variable labels. We could multiply both sides by y minus 2. Distribute the x. We could subtract y from both sides. Add 2x to both sides. Factor out y. And then divide both sides by x minus 1. And then finally, we relabel this as f inverse. And so that would be our answer. So any questions about that? All right. So let's take a look. We're going to get into logarithms. And so logarithms, we've looked at exponents. So the way exponents work is this. You have a base to a power is equal to some number. So a logarithm that goes with this is a log of the same base of that number is equal to that power. And that's it. That's all logarithms are. Another way you can think of it if you start with a logarithm and you want to get the exponent back, b to the p is equal to n. So if you go counterclockwise, base to the power equals the number. And that's how you can retrieve your exponent, or your, exponential expression, or exponential form. So let's just do a few examples. So 1/2. If you cube 1/2, 1/2 times 1/2 times 1/2, you get 1/8. So that means the logarithm, well, this is our b, this is our p, and that's going to be our n. So 1/2, 1/8, 3. So that's how we do our logarithm. Questions about that? All right. So again, something maybe not as complicated. 7 squared is 49. So log base 7 of 49 is equal to 2. And again, that counterclockwise trick, 7 to the 2nd power gives you 49. Now, the thing about logarithms, they're the inverses of exponents. That's what's going on here. Now, we do make some caveats here with the base. Just want to mention this real quick. The base is greater than 0, and the base is not equal to 1. Just want to mention that real quick. Now, to show that they're inverses, what this means. So let's say that f of x is b to the x, and g of x is log base b of x. Do something like this. So what's going on here? Well, let's start with f of x. Well, if we put this in logarithmic form, our base, our power, our n. In fact, let me put it in a little more. It gives a bit of a clue. Base, power, number. So that means the logarithmic form will be log base b of our number is equal to x. Now let's keep in mind, logarithm b is g of x. Except instead of having plain x, we've got f of x. So this means we're inputting f of x, and that gives us x. So g of f gives us x. What about f of g? What does that give us? Now, let's see. So log base b of x is g of x. So if we put this in exponential form, we get b to the g of x is equal to x. Again, b to that power gives you that number. But this looks like f of x. The only difference is instead of having x here, we've got g of x. So this means we have f of g of x equals x. And there we go. You can see that these are, in fact, inverses. Questions about that? So what are the consequences? Well, what this means just checking the time. B, we had b to the x. What if we had b to the log base b of x? So we have f of x. Instead of having just x, we have g of x here. the exponent and the log cancel out. Just have x. Likewise, log base b, here's f of x, that is just x. Again, the log and the exponent base are going to cancel out, and we get just x. Questions about that? So let me talk about the natural log. So there's typically two types of logs in your calculator. We're going to get to some more log properties here, but these are the inverse properties. So on your calculator, if you see this, that's log base 10. And on your calculator, if you see this, this is log base e. Now, e is a number that, and I'm not rounding it, I'm just listing some digits, and it goes on and on forever. But it's a number that's about 2.718, I think. It just keeps going on and on forever. So here, let me get the exact, a little more better approximation for E. But that's what you're going to see on your calculator, and that's what they mean. Now, you might be kind of wondering, well, hold on. What if I want to do something with, say, a log base 3? Or a log base 1/2, or a log base 7. Well, what do we do? And there's a way you can handle this. Let me see, I don't think they're giving it. There's another way of doing this. So it's about, I'll give you a little more of an approximation. When it goes on and on. So there's a trick with logarithms you can do, and this is one of the big properties. And I'll show you some of these. So logarithm properties. A really important one. Log base b of x, you can rewrite it as log base a of x over log base a of b, or how they express it in the book. You could also say the natural log of x over the natural log of b. So for an example, let's say you have the log base 1/2 of 1/8, and you want to do this on a calculator. So what you could do, this could be the log of 1/8, which is log base 10, divided by the log of 1/2, and this will be equal to the natural log of 1/8 over the natural log of 1/2. Either way, either one, you'll still get the answer 3. So this lets you come up with logarithms of bases that aren't showing up on the calculator. So any questions about that? It's a nifty trick. So other properties. Let's see here. So I'm using a slightly different format than the book. So log base b of m times n, log base b of m plus log base b of n. The log of a product is the sum of the logs. And again, the bases here, they need to be the same. Log of a quotient, log base b of m minus log base b of n. The log of a quotient is the difference of the logs. And there's a version of this. First off, log base b of 1 is equal to 0. And you can see this using that counterclockwise movement, b to the 0 equals 1. There's a kind of a extra bit here. If you take log base b of 1 over n, well, that's log base b of 1 minus log base b of n. That's going to be 0. You're going to get that. So finally, they have one called the power rule. If m has an exponent, that hops down in front of the log. So one last one that comes up, it's going to be this. So let's say we have this. Something like this. Well, what we can do, just like this jumps down in front of the log, it goes back the other way. We can put it back up here to get that. So here's E at 2.71828 number, goes on forever, irrational number. So this X becomes an exponent to that A. And the natural log well, that's log base E. So the base cancels, the log cancels, because the log and the exponent have the same base, the exponential expression. And that just leaves a to the x. So questions about that? So here, I'm going to do an example. So let's say we have this. And we're supposed to come up with another expression for this. Let's break it down a little bit. A log, and that's just a log base E. We have this here. So there's a couple ways we can handle this. We could say that this is a log base E of E, so they're going to cancel. Now this is going to pop down. And when these cancel, we're just going to be left with e. Now, technically, this is e to the 1, but you can just cancel these two. So you could say there's a 1 that's left here. We'll do that. We'll be thorough. In fact, I'll put that invisible 1. We don't even need to actually bring this e down. We could just cancel these two, and this e is what would remain. Let's say we did it this way. So natural log of e times 1 is e. And again, that's log base e of e, and again to the first power. So that leaves us cancellation in just the number 1. Questions about that? And if any questions come up later, let me know or send me a message. All right. So let's say we have this. Okay. So let's say in this case we're solving for y. How do we do that? Well, one thing we can do, let's make the ln of y an exponent of e. First, what we do to one side, we have to do to the other. So here, the exponent and the log, they're going to go, or the exponential expression or base, they're going to cancel with each other because this is log base e. So then we're left with y equals e to the 2t plus 4. And that's going to be our answer. Questions about that? So the last thing to mention in this chapter, I'm just going to go over it briefly, and it's with inverse trig functions, because inverse trig functions, if you're coming out of trig, you've seen these recently, but we'll do a little work on them. And what I'm going to focus on is the sine function. So it works like this. We have a sine, or we have, let's say we have an angle. If we take the sine of that angle, we're going to get some number. And if we take the sine inverse of that number, we're going to get an angle. So while sine will convert an angle to a number, sine inverse converts a number to an angle. Now there's a problem though. Remember we talked about the horizontal line test, that if the inverse is going to be a function, then the original function has to pass the horizontal line test. Well, let's take a look at sine. You can tell so this is y is sine of x. This fails the horizontal line test. So this means the inverse of this would not be a function. Well, we're very keen. We really like having inverse trigonometric functions. So we're going to do something. We're going to limit the sine function to an interval of the x-axis where that part of the sine function passes the horizontal line test. Abbreviate horizontal with just H line. So in math, this is what we've agreed upon for the limitation of the sine function. It's going to be this. So this is our limitation. We limit the domain, so it's between negative pi over 2 and pi over 2. And now, we pass the horizontal line test. This is the same thing that they do in the textbook with y equals x squared. They limit the domain, so it's just x greater than or equal to 0. So y equals x squared with x greater than or equal to 0, that will pass the horizontal line test. It just gives you the right half of that parabola. We're doing the same thing here with sine. So this is how it works. So what we're going to do, we're going to take a number. And it goes into the sine inverse function. And what's going to come out of the sine inverse function? Because remember, well, here, let me get a little ahead of myself. So this is what we're going to do. We'll swap domain and range to get the sine inverse. So that's one of the things we do with inverse functions. They take the numbers of the domain and they turn them into the range for the inverse, and then the numbers of the range for the function become the numbers of the domain for the inverse. So that means this is our y equals sine inverse of x. So instead of the sine x that had a domain from negative pi over 2 to pi over 2, now the range of sine inverse is negative pi over 2 to pi over 2. Instead of the range of sine being negative 1 to 1, that's now the domain of the sine inverse. Domain negative 1 to 1. So now I can explain what's going to go on. So if you input a number from -1 to 1 into the sine inverse, so here's the domain of sine inverse, you're going to get an angle from -π/2 to π/2. Similarly, we do something with, say, cosine, except cosine, we don't limit its domain to -π/2 to π/2. We limit its domain from 0 to pi. So for cosine, it's going to work like that. So again, you pick a number from -1 to 1, including -1 or 1, put in the cosine inverse, it'll give you an angle between 0 and pi. So to just do an example, let's say we have this. So sine inverse of -rad3/2. So what this means, we're looking for the sine of x equals -rad3/2, where x has to be a number in that interval. So we can reword this. So you can think of it like this. If sine inverse of -rad3/2, you can sort of attach equals x here. This is the same as saying sine of x equals -rad3/2, where x has to be an interval, or a number rather, in this interval. And so that's going to be -π/3. X will be -π/3. Questions about that? All right. Let me do one more. So 1/√2. Again, you can attach an equals x here. So we can rewrite this as not really a cosine inverse. We can rewrite it as the cosine of x equals 1/√2 for x. And now for cosine, we have to choose an angle between 0 and pi, including 0 and pi. Well, that angle is π/4. Questions about that? So the only thing I'll mention, there's some identities here, and I'm just going to point them out. So you have the cosine inverse of x plus the cosine inverse of negative x equals pi. And then sine inverse of x plus cosine inverse of x equals pi over 2. And that's going to be it. So that's going to move us on to section 2.1. In section 2.1, what we're getting into are two different ideas. One is called an average rate and an instantaneous rate. So the first is the average rate. And we typically, we're going to be, so we're talking rates, we usually deal with time in this, we don't have to. Let's say we have this. So let's say we have this. We define the average rate. So we have these 2 points. We want to find the average rate of f of t, the average rate of change for f of t from t0 to t1. And this is how we define it. It's the change in y over the change of t, or it's just your slope formula. y1 minus y0 over t1 minus t0. So it's just the slope of a line that intersects these 2 points on the curve. We can call it average rate of change. Sometimes we call it average speed. All right. So I'm going to run through an example. Say we have this. So f of t is 16t squared. And what we want is the average speed from t equals 0 to t equals 1. So let's find out what f is at t equals 0. So for t equals 0, f of 0 is 16 times 0 squared. Well, that's just going to be 0. For t is 1, f of 1 equals 16 times 1 squared, which is just 16. So delta y over delta t, or 16 minus 0. Well, here, I'll be a little more specific. Still go with y2 or y1 minus y0, t1 minus t0. It doesn't hurt the labels. You see what you're doing. d0, y0, t1, y1. T1 will give you y1, T0 will give you y0. So we'll get 16 minus 0 over 1 minus 0 or 16. So if you choose two different points, though, you're going to get two different results. So let's change this up. So same question. So let's go from t equals 0 to t equals 2. Well, in that case, we know t equals 0. That's 0. T equals 2. That's going to be 64. So now we do our formula. Get 32. So the difference is this. The thing to keep in mind is 16t squared is a parabola. So when we choose different points on this parabola, we're actually getting different lines. So for example, steeper than that. So let's say this is 0, and that's 1, and that's going to be 16. It's kind of hard to see, I'm sorry. So this is 1, and that's 16 on the y-axis. So we're finding the slope between these 2 points. We're going to get a line like this. Let's see if I can make this a little bigger. This is the 16. That's 1. But so at 2, it's 32. Here's 2. This line, because we're going, starting with t is 0, y is 0. So we're always starting at the origin. This line has our steeper slope. So a little terminology. These lines are called secant lines. So this passes through the curve at 2 points. And so the secant lines in this graph, this secant is not as steep as that secant. So the point is this. As we change the second point, instead of being t equals 1, make it t equals 2, we get a different point on the graph. We get a different secant line, and the slope of that secant line is going to be different. So it turns out the slope of the secant line is the average speed. And you can see this from how we're calculating the secant. This rate of change. The slope of the secant line it's the same formula that we use to calculate the slope of any line. Okay. So questions about that? So what we're going to do, we're going to take kind of a little bit of a leap here, but not a very big one. Hopefully not too big. So we're going to change this a bit. Again, if we're going too fast, let me know. But let's say we do this. So we've got our points again. Let's say the distance between t0 and t1 is a distance of h. So this means t1 is equal to t0 plus h. So this is what we're going to do. This changes our formula. So delta y over delta t is equal to y1 minus y0 over t1 minus t0. Now what we're going to do, this is really f of t, this function. So y1 is f at t1. And y0 is f at t0. So let's make this replacement. T1 is T0 plus H. So this is T0 plus H minus F of T0 over now T0 plus H minus T0. So the T0s here, those are going to cancel. T0 subtract T0 is just 0. So we're going to get this. F of T0 plus H minus F of T0 divided by H. So this is an alternative formula for the average speed, where H is the distance between T0 and T1. Or you could say T1 equals T0 plus H, either way. I'll just keep it because that's what we used last time. I'll keep it like that. So this is an important idea. So what we're going to do, let's find the average formula. The formula for the average speed of 16t squared. We have to make one caveat. We do need to state what T0 is. We do need to state that. So what we're going to do, we're going to use our formula. F of T0 plus H minus F of T0 over H. So what this means, we have 16 times T0 is 1, so that's 1 plus H, minus 16, oh, this is squared, times 1 squared, over just H. So instead of having a T0 and a T1 to juggle, we just, if you put a number in for H someday and you know what your T0 starting is going to be, you're good to go. Now this we've got a FOIL. Distributor 16. The 16s will cancel. So what we'll get, 32H plus 16H squared over H. Or divide the H, we'll get 32 plus 16H. And that's going to be our answer. Questions about that? All right. So what we want to talk about, we've got 10 minutes still to go. We go over this. So we've talked about these secant lines, and we talked about what's called the average rate or the average speed. Now we want to talk about instantaneous rates. So the average rate or the average speed is the slope of a secant line. So the average rate between these 2 points would be the slope of the secant line. So that's the average rate. Now we're going to talk about instantaneous. The instantaneous speed is the slope of a tangent line. And the difference is going to be this. A tangent line contacts that curve at only one point. Kind of hard to see here. Like this. So it contacts the curve at only one point. So how do we come up with this? Because to come up with a slope, we always need 2 points. So what we're going to do, let me illustrate. A little different arc here. There we go, a little better. So let's say we have point P. What we're going to do, we're going to start with a point Q. And what we're going to do, say this is T0, and this is T1. And let's actually just do it a little bit differently. Sorry, I keep doing board surgery here. Make this point P. There we go. So you have a T1, T0, Y0, and Y1. So what we get is that secant line. We do get this. And the difference here is going to be h. But then what we're going to do, we're going to move Q over. So now, this is our T1. This is our new Y1. and that's our new h. Then we're going to move q again. We get a t1, a y1. And then really in here, this small little space here, we're going to get another h. So let's take a look. In summary, this is what's going on. Q is getting closer to P. As Q does this, Y1 is getting closer to Y0. And T1 is getting closer to T0, because here's T1, 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 there's our T0. And then H is getting smaller. So as Q gets closer to P, Y1 gets closer to Y0, T1 gets closer to T0, and H is going to 0. It's shrinking to nothing. So questions about that? It's a little messy, I admit. So here's the idea. If you want to see a good picture of this in the text, so I'm going to do one example, but that'll be it for today. Let's see, I might even draw my own and post that for you later. So let's say this. Find the instantaneous speed for y equals 16t squared at t0 is equal to 1. So what we do first is we first compute the average speed formula. So to find the instantaneous speed, we're going to compute the average speed formula first. And we found out what that was. Let's see, remember what that was. It was 32 plus, let's see, 16h. So this was from before. So finally, this is the only thing we need to do. For the instantaneous speed, as Q gets closer to P, H goes to 0. So we get 32 plus 16 times 0, or 32. So when doing this type of problem, you're doing most of your heavy lifting in this step. You're going to compute the average speed formula. And then once you've got that, to get the instantaneous speed, just let h be 0. And there you go. And so that's the two things with rates. And I'll make another graph. I'll post one up there because I think this is a neat idea. But that's going to be it for today. If you have any questions, let me know. I might post some extra examples, like some of the story problems can get a little complicated. So I might do some of those and post them just so you have them, something to work with. other than that, that's it. We're in chapter 2. We're getting in the limits. We actually just computed a limit. So, all right. Other than that, have a wonderful day, and I will see you on Wednesday if I don't hear from you before.
Thank you, Professor.
No problem.